So, as Dr. Pringle said, I'm Michael. I will be talking about the maximin consensus of agent preferences using heuristic search. So just a quick kind of background on preferences in general, because you all might not be familiar with it. Preferences are just ways that we express that things are better than other things. So for example, if we had three things, A, B, and C, we could order them, say A's first, B's second, and C's third. We could do B is better than A, is better than C. Obviously, it would be like C in this example. Or we could, in fact, say that things are roughly equivalent. So like here we have that A and B are roughly the same. I don't care which one I get, but as long as I don't get C. So the research that I'm doing deals with what are called combinatorial domains. And the idea is that in a lot of cases, we don't have three items that we want to order. We have 1,000 or 100 or 6 million, right? And so we wanted to be able to describe these things in kind of a compact way, because listing out 6 million things in a linear order is going to take a very, very long time. Not to mention it's probably going to annoy whoever I have to get the 6 million items from. So what we do is instead we represent them as tuples, and those tuples have as their elements values for different attributes. So kind of a quick example, if we're trying to buy cars, we can categorize cars by whether or not they have seat belts, whether or not they have 4 doors, and whether or not they have air conditioning. So in this particular example, all these things are binary. So it either has seat belts or it doesn't. It either has 4 doors or it doesn't. And of course, it either has a C or it doesn't. So when we look at this domain, since they're all binary, we can represent them as either a 1 or a 0. So for example, if we have 1, 0, 1 as our tuple, we have a car that has seat belts, is not a 4-door, and has a C. And what this allows us to do is that in a lot of cases, we have an exponential domain size. So in this case, it's 2 to the 3, but we can imagine, say, 18 different attributes. That would be 2 to the 18th if they're all binary, and it balloons as such. But we only need 3 things to actually represent any one of the 8 different alternatives. And of course, it's also possible to have more than just yes or no on a particular attribute, right? We could specify, is it a 2, 4, or is it a minivan for doors, right? So now we have the issue of we have to express our preferences over these combinatorial domains. And of course, as I said earlier, we can't just put a linear order out there. It's practically impossible to elicit, and it's just super inefficient memory-wise. So we need a compact method of representing our preferences, the same way that we needed a compact method of representing the domain. So one way that we do this, and there are quite a few different methods for representing preferences compactly over a combinatorial domain. But one of the ways that we do it is lexicographic preference. So in a lexicographic preference, you order the attributes by how important they are. And then you order each of the domains of the attributes. So in our limited case is having the thing better than not having the thing, or vice versa. And the way that you compare 2 things is you consider the most important attribute. So we'll pick my example here. So first you would see whether or not they have seatbelts. If one has seatbelts and the other doesn't, then you're going to take the one with seatbelts. You're going to prefer that alternative. If, however, they both have seatbelts, or they both don't have seatbelts, basically if they're equivalent on our most important, then we'll break that tie by going to the next important attribute. So in this case, it's 4-door. So, right, we want something that's not 4-door over something that is. So if they both have seatbelts, but one has 4 doors and the other doesn't, we're going to take the one that doesn't. And if they're both tied at 4-door, then we will finally consider a C. Otherwise, if they're equal on all 3, then they're equal in our mind. And so you get an order that looks like this. So as you can see, everything with a 1 in the first place, which is our seatbelt, is better than everything with a 0. And another interesting thing is that lexicographic orders produce what are called total orders, which means that everything can be compared to everything, and there's a strict relation between the two. So if I give you car A and car B that are somewhere in this domain, you can tell me, car A is better, or car B is better. So another preference representation, and one that is specific to this research, is what's called a preference formula. And the idea is that instead of saying, oh, I think this is the most important thing, and then this is the next most important thing, you describe logically desirable properties, right? So our example here, the preference formula, just for shortness, A is seatbelts, B is four-door, and C is air conditioning. We prefer anything that satisfies this first expression. So anything with seatbelts is better than anything at all. Anything else, anything that doesn't have seatbelts. And then, if it doesn't have so that would give it rank 1. So it's the best. And then, if it is a four-door and it doesn't have AC, it would be second best. It would be rank 2. And then the T at the end is just true, which means that anything that doesn't fit in these first two categories, just lump it all together into the C. Right? And so, if we are to evaluate this over the entire domain, because there are only 8 we can do that, we get a non-total order, total pre-order technically, which says, okay, these things are roughly equivalent, but they're better than these things and these things. And these things are equivalent, but they're better than these things. So we can ask if two things are strictly better than one another, but we're not guaranteed to get back a yes. Or we can get back that they're equal, right? So according to this, if I have seatbelts, four doors, and no AC, it's the same to me as if I have seatbelts, no four-door, and I have AC.
Can you read that formula in English? I don't know how to parse it.
Okay, so it's things with seatbelts are better than things with four doors and no AC, which is better than everything else.
Okay.
Okay, so now we come to this idea of consensus. We're finally getting to the fun part of it. And the idea is, let's say we had multiple agents. Let's say we had a family that needed to buy a car, right? So everybody in the family is probably going to have different opinions on what's a really good car to have. And so it would be really nice if we had a representation of their preferences that stitched together all of their preferences while trying to satisfy everybody. So basically the best middle ground representation of their preferences so that we could then decide a car for them, right? So this is what the research is looking at doing, and in order to be able to do this, we have to know what does it mean to satisfy an agent. Because if we don't know that, then what are we trying to accomplish? So for this research, the way we score it is, let's say we have this comparison. And that's going to come from our joint model, right? So we have that comparison. So what that means is each agent is awarded 1 point of satisfaction if they also have that same comparison, right? So this means that the more comparisons that the joint model satisfies for each agent, the higher that agent's score. So now we have a whole bunch of scores for a whole bunch of agents, but we need some way to combine them, right? So the kind of like first shot that most people would go for is that why don't we just add them all up, right? A higher number means that we have more comparisons satisfied, which means obviously it's a better model.
I have a question here.
Yeah.
You do all the possible comparisons that you have through the third, the domain through the third, you have that squared approximately comparisons.
Yes, we mitigate that later in how we elicit preference information from the agents.
Okay.
But yes, in theory, we would have a lot of comparisons to deal with. But anyway, back to the add-them-all-up scoring model, or also called the utilitarian model. We can have a situation wherein one agent is disproportionately satisfied, right? So if I prefer ABC and Dr. Finkel prefers CBA, then in every case we disagree. And so there's no, if we do utilitarian scoring, we could just go with ABC, and Dr. Finkel's completely satisfied, and that gives us a high number. And I'm completely dissatisfied, but we still have a high overall number, right? But it would be better if Dr. Finkel got half and I got half, right? I think everybody here.
I don't think so.
Yeah, right. It depends on who you are in the scenario, how much you like that. But we would like to have all of our agents roughly fairly satisfied, right? That's a good goal. And so one of the ways that we can do that is by scoring using maximin. And the idea of maximin is that the score for the joint model, the satisfaction score overall, is how many comparisons it satisfies for the least satisfied user. And what that enables us to do is if we maximize that, that means that the least satisfied user is as satisfied as they're going to be. Sorry, agent. So everybody may not get their best possible satisfaction, but everybody will be guaranteed a certain level of satisfaction.
So, Mike, does that imply that the larger your group of agents that you're trying to satisfy, the lower, least satisfied agent's score will be?
Typically, yes, because more people, more disagreements, right? But we would expect that in anything, right? If you get more people together, more people are going to have more disagreements unless everybody thinks exactly the same way.
Actually,
So just an example, if we use the two agents that I used for the preference type examples, and we use a preference formula to try and give us a joint consensus model. So if we consider, let's try this really simple preference model, right? A is better, seatbelts is better than not 4 doors, which is better than having a seat. So, our lexicographic agent from before, we get a score of 21. And our preference formula agent, we get a score of 16. Now, this is based off of all of their possible comparisons, because we can do that if the domain is small enough.
I thought when you did the scoring, it was with respect to some joint model.
Yes, this is our joint model.
So show the two models. Yeah.
So this is our preference formula model, which is represented by that. And then we also have our lexicographic model.
Oh, okay, fine. So we have two models and we're now satisfying them both by this new model.
Yeah, we're attempting to satisfy.
Yeah.
So if we look at this first joint model, right, we have 21 for the lexicographic agent, we have 16 for the preference agent. So our utilitarian score is 37, which is pretty decent. But our maximum score is 60.
Where do those numbers come from?
So we count the we count the number of strict examples that are satisfied in both.
Yeah, thank you.
It's the number of cars that it's better than?
No, it's the number of times that I say, let's say you say car A is better than car B, and my joint model says car A is better than car B. Then that would count as a point of satisfaction for you.
Okay, so it's like the percentage of all the comparisons that your model says that I agree with is my judgment in your model.
Yes, but it's not a percentage, so don't.
But it's the total count.
Yeah, it's the total count.
So higher is that?
Yeah, we want better. However, if we look at this second model, which literally we just changed from not being not 4-door to 4-door, being our second rank, The lexicographic agent suffers a bit, right? There are 4 or less comparisons there's 4 less points than there. But the preference formula agent gets 2 more points of satisfaction. So the utilitarian score is 35, which is worse than the first one. But the maximin is better on the second one. Now, if you didn't know which agent you were, would you prefer to be in the first, have your consensus be the first one or the second one? My argument would be that you would like to be the second one because you're guaranteed at least a satisfaction score of 17 rather than 16. So this brings us to the general problem that we're trying to solve, which is how can we build such a maximin consensus preference model? I mean, we could throw darts at the dartboard, but that probably wouldn't get us very far. And our answer is find a good approximation using heuristic search. And if we look at the theoretical side of it, we have kind of 3 questions that come out of our overarching question, which is how do we get that preference information from agents, right? So as Dr. Finkel said, you've got something n squared and the n's exponential, so you can't have everything. But the other 2 questions are, is it computationally hard to find an optimal solution? And is it hard for a single agent as well as multiple agents, or just for multiple agents, right? So first, answering the first question, how we elicit examples. So basically, we just ask agents things. So we have these triples. And if I have a triple alpha, beta, and u, that means that alternative alpha is better than alternative beta for a user u, right? And so basically, you just ask the agent, hey, do you like A better than B, or do you like B better than C? And we ask them a specified number, and we get some information as to their preferences. And then we use that set to find the model.
Excuse me?
Yeah.
Is alpha and beta like in your example cars, or would it be preference formulas?
They would be cars. They're alternatives. They're options. So.
And how do you decide which elicitations to make? Are you going to talk about that?
There are several different methods. The one that we use, I will discuss later, which is essentially random.
So I will perhaps add that there are many strategies perhaps, but this where it doesn't depend on any or doesn't use any, somehow examples are elicited or observed, because they could also be observed, and they are at least in learning.
Okay. So back in the theoretical considerations, if you want to tell how computationally difficult something is, it's probably good to have it as a decision problem. So this is the problem as a decision problem, which says that we have a set of examples epsilon, a set of agents A, and a positive number k. And we want to find a consistent set of examples. And what consistent here means that if we say that alpha is better than beta, that we can't somehow derive that beta is better than alpha, so there aren't any conflicts in that sense. And we want to see if there is this epsilon prime that's a subset of epsilon, and that the number of satisfied examples for an agent is at least k. So that's the decision version of the problem. That's the formal definition. And in the single agent case, we just basically remove A because we only have one agent, and we just say that epsilon prime is a subset of epsilon, and it has to be greater. So I guess unfortunate result from this is that both the multi-agent and the single-agent problem can be shown to be NP-complete. So they're computationally hard. We can't just attack this with an algorithm that will run efficiently and be done.
Michael?
Yeah.
Can you show the problem again?
Yeah.
And so I thought the problem was to construct an ordering, not to come up with a subset of the examples.
Correct, but this is the more general problem.
How is there a correspondence there? How does having a
so
subset of examples?
in our case, we are using a preference formula, and it is theoretically possible that a preference formula can express any possible preference relation that is consistent, according to our definition of consistent. Now, that preference formula may be very large, right? It may be, in fact, a linear ordering of our alternatives, which is bad, but it's possible. And so any consistent example, any consistent set of examples can also be represented by a preference formula. And so the overall, like the underlying general question is, can we find a consistent set of examples such that we guarantee a certain performance variation?
Oh, okay.
So
That
that's
makes
your
sense, yeah.
question, or did that confuse you?
No, it makes sense now.
Okay.
Okay.
Right. Yeah, so both the problems are going to be complete. If you have multiple agents, it's the same as if you have a single agent. So we tried to tackle it 3 different ways. The first was to convert to answer set programming. I'll define these a little bit more later. Was to convert to answer set programming, which has some nice properties. It gives us some nice guarantees. And then moving on from that, attempting simulated annealing and using genetic algorithms. So before we dive in, we did restrict our models for this attempt of learning these preference models. So the first thing is that we said that every rank, which is rank A, better than B, so on and so forth, it's going to be represented by a disjunctive normal form logical expression. So that means that you have things united together and then those units are ordered together. And then we decided to limit the number of disjuncts, so that's the number of units with ANDed literals. So we have a bound on that. We have a bound on the number of literals in each disjunct, which are ANDed together. And then we bounded the number of ranks. This was all to make the learning a little bit easier, because like I said, we could have a very long preference formula that perfectly expresses any preference order. So here are some examples of what we consider valid. And so if there's only one disjunct, right, we have nothing here. This is a single unit, and it's not ordered with anything. And then we have 2 literals, which means we have these 2. And so like x1 would be the first attribute, x2 would be the second attribute. So in this case, we're also assuming that they're all binary, just to simplify the representation, so that it's not binary. And we have 3 ranks, which means that we have 3 expressions, and all the expressions are of the same form. And then, of course, we can get more complicated, right? If we have 2 disjuncts, then we have 2 of these ANDed things, and they're ordered together. And of course, we can just go real simple, 1 literal, 1 disjunct, everything.
Question.
Yeah.
So each of these things is one agent's internal preference?
No. These, well, they could be. But these are just describing the structure of the rules that we're trying to learn. So if we're trying to learn a 2 disjunct, 2 literal, 2 rank formula, it will look something like this.
Okay.
So it's just kind of a structure.
And it's a single formula then, modeling any person's preference, any agent's full preferences.
Yes, we use lexicographic preference for agents, and that will explain that.
Okay.
Actually, I think it's 3 or 4 slides. So the first thing that we did experimentally was is we tried using ASP, which is answer set programming. It's a declarative language. Basically, it allows you to put down a series of facts and relations and restrictions, and then you throw all that into a solver, and it comes back with solutions, if solutions exist. But there are quite a few drawbacks, which is anytime you try and scale this conversion, so you try to add more expressive formulas that you're trying to find, or you have more examples from users, or you add more agents to the mix, the runtime tends to bloat quite quickly. And so getting information out of ASP takes a very long time for anything that would be considered remotely useful. Right? So another one of the things that we tried was simulated annealing. So here's basically just a kind of very rough pseudocode. You start out with the temperature that just determines things later on. You basically choose a random model. So we choose a random formula and we say, okay, how good are you? And then we choose one of its neighbors. In this case, we would be determining a neighbor as a change in one of the literals. And we grab a random neighbor and we say, is that neighbor better? If it is, we go ahead and take it. If it isn't, then based on what our temperature is currently, we may take that neighbor which doesn't give us any improvement, or we may just leave it there. And then at each step, we reduce the temperature, and of course all this has a million parameters that you can twiddle with if you really wanted to. But at the end, we eventually reach some sort of stopping criteria, whether that be the temperature is sufficiently low, or we've done this a million times, let's go ahead and stop it already. And then we just take that model that we have. And of course, the other, and this being one of the heuristic search techniques, the other heuristic search technique that we use is a genetic algorithm. Basically, you take a whole bunch of random models, you evaluate them, and then you pair them together based on their performance. You combine those pairs, and you come up with the next generation of formulas. And you do this until you've done it a million times, or you've reached some level of satisfaction that you're picking.
And the mutation step is in the combine?
Yeah, you combine and then you mutate. So, there are good properties that we can exploit. Like a lot of these algorithms tend to be focused on large search spaces, right? So there's a lot of things with using genetic algorithms and simulated annealing to deal with potentially very large search spaces and finding good approximations. Generally speaking, we found that they focus quickly onto promising areas. Now this is obviously not optimals, but usually some sort of maximum or minimum, depending on what. The runtime scales much better than ASP. With more complicated models, it doesn't take significantly longer. So in that way, we can scale this to practical examples after we're done with experiments. We can modify these things to make them a little bit more specific, right? So we can tailor them to our specific domain if we want to add in some a priori knowledge. It also, now they don't have to have a constant model size, but for our purposes, we're considering a constant model size, just because it means that we can kind of zone in on how well does this particular type of formula do. And of course, that means that they're also pretty well structured, which means that mutating them, dealing with them, finding neighbors is a relatively efficient thing to do. And also, kind of the most important is that complex evaluation is very easy to do. Instead of having to do a whole bunch of math and specific calculations for the fact that we're using maximin and this might change that, might change this, we can just tell it, go ahead and just evaluate it, because we can do that really easily. and then we can score you based on that. So, getting into our experiment. Our experimental setup, we started with agents that are lexicographic preference models. We did this because it gives us a total order, which means we can just throw two things at it, and it will always give us back a strict example. So it'll always say A better than B, it'll never say, I don't know. And we varied between 2, 5, and 10 agents. We stuck pretty succinctly at 100 examples per agent, and those were generated by saying, okay, give me a random alternative, give me another random alternative, what do you think about these things? Okay, thank you for your example. This is all synthetic, of course. We didn't actually ask people. And then, we specified how our preference formulas were organized. 1 or 2 disjuncts, 1, 2, or 5 literals, and 3, 5, or 7 ranks. This is some of these things will appear in some of the examples on the just forewarned. And generally speaking, we did 100 runs, which means we generated all of our agents, and we did that 100 times, and we generated, basically we had 100 different example sets so that we could get a good average of performance. And our domain remained constant throughout everything, which was 8 binary attributes, so we have 256 different alternatives that we want to vary. So, starting out in the beginning, to see whether or not we could even approach what the optimal is. So these optimals are the average over 100 runs. So on average, the optimal, and this is for 5 agents, the optimal was around 40 examples satisfied for the least satisfied user. And that was done using ASP. And what we found is that if you use simulated annealing or you use a genetic algorithm, you get decent approximations of that optimal, right? We're 80, 70. We're getting pretty good results, right? So we can get a good approximation from our genetic algorithm or our simulated annealing, and they run faster than ASP. And just as a general note, the genetic algorithm tended to always perform better than simulated annealing. 100 examples, usually about 3 times the simulated annealing would be better than the genetic algorithm, which means that we focused in on the genetic algorithm kind of as our primary research.
I have a question.
Yeah.
So what you're creating is not total ordering, right? It's like the official term is total reorder. But if mine is strict and yours is not strict, then how do you add it up?
We only consider strict examples. So if you say that A is you wouldn't say that A is A. If you say A is better than B, and my model says we just don't count it as a positive example.
Okay, so it's only when you strictly agree.
Yes.
That it counts for.
That was it. Now we're looking into that a little bit more, but the research is completely done. Now, if we focus in on the genetic algorithm and take a look at how it evolves, so, right, we've got 2 agents, 5 agents, and 10 agents. We still got that 100 examples per agent, but we're only looking at the genetic algorithm in this case. And so, as our model gets more and more complex, this is disjuncts, this is literals, and this is ranks. As we get more and more ranks, we get better and better scores. And as we get more and more agents, we get worse and worse, which are kind of the trends that we would expect. And so we just kind of see what we would expect. We're relatively convinced that these are somewhat close to optimal, considering our previous experiments. And I guess the real key thing is that each agent gets around half satisfied with our approximation. That means half their examples are properly represented in our learned preference representation. And of course, we still have some further work to do. We're looking into, can we invent a greedy approach that will give us a good approximation, right? Is there an algorithm that runs in polynomial time that will just blow out of the water the genetic algorithm and simulated annealing, or at least give us a close enough approximation to optimal that we don't need to bother with heuristic search. And then of course we're also looking into modifying our heuristic search and seeing further modifications to the domain of alternatives. So more options per attribute, more attributes, right? So again, extending it to like, let's have 18 different things rather than just 10. And that would be all I have.
Well, I think we'll take questions offline at this point so that I have a chance to say something.
Yes.
And I told Michael before I take as much time as you want, because this is more interesting